I want to give you a basic introduction of what exactly are the practical application of steel structure buildings and how they are made. And this lecture is just to give you a clear idea of what exactly the present industry or the present practice in industry is for the steel structures. So basically why we are going for the steel structures, because for PEBs, that is pre-engineered buildings, we can save up to the 40% of this time, and early occupancy is there for the structure. It is also cost efficient, as the steel structure is very has a very scope of the flexibility or the expansion, so we can easily increase the structural capacity of the pre-engineered buildings, and they also require less maintenance, and they can also be designed for the earthquake and hurricane resistant. The quality of the pre-engineered building is very good, because all the structures or all the structural steel sections are prefabricated in a workshop, and they can also be relocated. So the number one component of pre-engineered buildings are the anchor bolts. So the purpose of anchor bolt is to anchor the complete total steel structure that is above the ground to the pedestal and to the foundation. And usually in India as well as in the US, the ASTM A36 grade is used. This standard is prevalent in the Middle East also, in India also, and in US also. So ASTM A36 is basically the code, and these are the basically L-shaped bolts here. There are also J-shaped bolts, and the plate. Basically the plates are welded with each other to form the structural steel sections. And for pre-engineered buildings, we use 345 MPa structural steel grade. So this is also a thing that is not known by many people. This is basically the profile that can be used with the help of the plates, and the plates that we use for structural steel for the pre-engineered buildings is most of the times of 345 MPa yield strength, and this is the code that is ASTM A572 for a reference of the grade of plates. And these are the simple these L-shaped sections. So for the simple L-shaped sections, these are the hot rolled, and IS 2062, that is Indian standard, can be referred, and the grade of these type of L shape is basically 245 MPa. These are the cold form sections, and HR means hot rolled sections. So for these cold form sections, basically we can have C purlin or Z purlin. So the thing that you need to note here is that the complete this structure, steel structure, can be made for the these prefabricated plates. But when we talk about the purlins, or when we talk about the girts, that is side purlins, then we can either go with the Z-shaped purlin and C-shaped purlin. And the C purlin and Z purlin are too much economical as compared to the simple hot rolled purlins. And they are also 345 these MPa yield strength or 450 MPa yield strength, and they are pre-galvanized. And the thickness can vary from 120 GSM, that is gram per square meter, to 275 gram per square meter. These are the simple connection bolts, and ASTM A325 can be referred. These connection bolts are usually of the grade 8.8, and the simple sheeting that is installed on the top of the structural steel building, the ASTM A792M, needs to be referred. And these are galvalume sheets. You need to remember this term, galvalume sheets of yield strength 355 to 550 MPa, and the thickness can be 0.5 mm to 0.6 mm. And this is the deck sheet that we had initial discussion in the previous lecture also, when we were designing the composite steel structure. So for these deck sheet, ASTM A653 needs to be referred. They are usually galvanized of thickness 120 to 275 GSM, and the yield strength of these deck sheets is in the range of 240 MPa to 345 MPa, and the thickness in the market starts from 0.6 mm to 1.2 mm. Now basically now we will discuss the construction methodology of the multi-story steel structures. So first of all, we erect the structural steel columns. After that, we install the beams here. Similarly, the beams to close this whole arrangement, and then we install the secondary beams here. On the secondary beams, similarly we can complete the whole arrangement here. This is basically the tower crane that is being shown here. After that, here you can see that now the deck sheet has been installed. So similarly, the complete deck sheet arrangement has been installed here. So now you can see that basically we have poured the concrete all over the deck sheet, so that the complete RCC slab is formed here. Similarly, we now go to the upper floor, then we install the main beams or primary beams connecting the columns to columns. Then we install the secondary beams here again, and then we again install the deck sheet, and then again we will do the concreting here. So basically I want to repeat this whole arrangement again. First of all, we erect all the columns in our steel structure. Then we cast the main beams or erect the main beams. Then we erect the secondary beams. Then we install the deck sheet arrangement here. Now after installing all the deck sheets, we pour the concrete all over the deck sheets. Then we again install the main beams of the second floor. Then we again erect all the secondary beams here. Then we will again install the deck sheets with the help of stud bolts. And then again we will pour the concrete. Similarly, we can go to the upper floors also. So in steel structure, erection methodology is also a very important step, and as a structural engineer, there is this thing that you need to do, is that you should check the structural stability of the steel structure in each and every stage. That is, at a stage when the concrete is poured only on these two floors and there is no concrete over all these three floors. And in all these three floors, a live load may act for the worker maintenance or the worker erection loadings. So these type of arrangement, you need to do various permutation and combinations, and accordingly you need to design the steel structure here. So here you can see that now the concrete has been poured all over the floors here, and now the complete steel structure has been built. So here on the top, basically the space trusses are installed. And on these space trusses, because these are basically the cantilever trusses, so on these cantilevers again now we have poured the concrete all over them. So same as the arrangement here, just to give the architectural elevations. And then again we can pour the concrete over the upper floors, and on the top we can install the helipad. So these are the various practical steel structures. This was just an animation, but these are the practical steel structures here. So here you can see that basically these are the RCC columns, and these are the these are the steel columns, and these are the steel beams. And over these steel beams, the deck sheet has been installed here, and here you can see that these are this is basically the main beam, and these are the secondary beams. So basically what is happening here is that this is basically the RCC column and this is the steel column. So the connection has been made between the steel column and RCC column with the help of the anchor plates, or it may be insert plates. So here you can see that the steel column has been erected here, and accordingly the steel beams are also casted here. And here you can see that this is the splicing joint here. That is, the steel column, the length of the steel column is usually in the range of 12 meters. So after 12 meters and another steel column is made, and then again after 12 meters and another steel column has been made, and the connection between these two columns is with the help of this splicing joint here. So again here you can see that the same type of arrangement has been made here. Here you can see that basically the steel columns are started from the RCC columns here. So there must be a base plate here. And this is also an example of a steel composite deck slab here. Here again you can see that basically one-way panels are made here, and here you can see that these are the sag rods. So in the next lecture, when I talk about the sag rods, you should get a clear picture of what exactly are they, and they are basically made to tie the these portal frames in the plan view. And here you can see that basically the profile of the steel beam is going like this. So here, as I had discussed with you earlier also, that is negative moments comes on the top. So negative moment is always greater than this positive moment. So that is why here you can see that the depth is high, and here you can see the depth is low. Here also you can see that the depth is higher in the when we are connecting beams to the columns, and the depth is lesser here. And here you can see these are the cold roll sections. So in this arrangement, these are basically the blue color is basically the hot rolled structural steel sections having 345 MPa yield strength, and these are the cold rolled C purlins or Z purlins. Here again, this is an example of a steel structure, and here again it is a steel structure. So in this multi-level car parking in this Lulu Mall in Cochin, this is also basically this whole car parking is made in a steel structure. I have been to like this mall, and while using this mall you won't get a feel that this whole this parking is made in the steel structure, but when you will see the images, then you will come to know that how like an engineering can be that good in execution. So here you can see that these are basically the splicing joints here, and these are the deck sheets. Here also you can see that these are basically the stud bolts, and the deck sheet has been laid here. Here you can see that these are basically the truss sections that has been used. So on the top of the truss sections, these C purlins has been used, which are in the cold roll structural steel sections. So this is also a very good example of a steel structure. There are very large cantilevers here, and there are very large spans. And how we can handle these large spans? We can handle the large spans with the help of this built up structural steel trusses. So many of you might be thinking that why we are not using these hot rolled structural steel sections like ISMP 500 or NPB 500 or UB 600. So basically the advantage of using this type of arrangement is that you can reduce the weight drastically, because these members are maybe this MC 100 or MC 150 tied with the help of this either angles or channels. So with the help of this approach, we can reduce the weight of structural steel a lot. And here also you can see that the basic skeleton frame has been erected here, and after the erection of the steel skeleton, we can just tie the secondary beams, and then after that we can do the casting. Here also you can see that there are very large or very like strong built up eye sections here. Similar is the case here. Here you can see the erection that is going on here. So this is basically the mobile crane, and this is called the counterweight, and this is called the boom. So here you can see that the length of the boom is very high. So this is like there must be a trailer here, or this basically the purpose of this crane is that from the trailer this crane picks up this truss, and it erect that on the site. So this is basically the ITC Bangalore construction, and again this is a steel structure construction. Here you can see that basically these are the stiffeners, and this is basically the connection here. So here you can see that there is a very 100 mm cleat or a 75 mm cleat, and they have provided 1, 2, 3, 4 and 5 number of maybe 16 or 20 mm bolts here. So usually the grade of these bolts is 8.8 itself. We don't use 4.6 grade of like bolts in the structural steel construction. And here also you can see the stiffeners. These are the columns. These are the steel beams, and here you can see clearly the deck sheet arrangement here. And as I was discussing with you earlier also, that grooves needs to be perpendicular to or parallel to the shorter span here. So this is basically the groove from this point to this point, and it is parallel to the shorter spans. And here also you can see that GMI Projects Platina Hyderabad, there is large scale steel construction going on here. And here you can see that they had provided the plan bracing here. They had provided very large or high depth girders here from this point to this point, that 1, 2, 3 and 4 girders. They have tied these girders along the shorter span also, and they had provided a cross bracing here. And on this girder they had provided a stub column here. And after providing stub column here, you can see that they have provided 2 stiffeners here, because after providing these stub columns, the shear force here is very high. So these are the like regular practices that keeps on going in a structural engineer's mind. And here also you can see that this is a very I should say 1, 2, 3, 4, 5, 6, 7, approximately 7 to 8 G+10 story building. And this is also made in the structural steel. And this is basically the airport, and most of the airports are usually made in the structural steel itself, because in airports we are dealing with the very large spans. And here also you can see that the span of this truss is very high, that is from this point to this point. There are no intermediate supports here. Similar is the case with this truss. Here also you can see that one support is here, and then another support is very far away. So this type of construction can only be made in the structural steel. We cannot make this type of large spans in the RCC. We can make them, but that like proves to be a very costly construction. So here also you can see that how beautiful this truss is. From this point to this point, we have provided intermediate supports here, and accordingly where the requirement of depth is high, that is forces are high, the designer has increased the depth of this truss, and where the forces are low, the designer has decreased the depth. So these are some examples of the structural steel sections or structural steel buildings that are usually made in India. And after that I want to give you another brief explanation. There is also another approach of making the composite steel decks called speed floor. So why it is called speed floor? Because it is a lightweight and cost effective system, and it reduces the time of the erection. So basically there is no need of the like making a scaffolding arrangement below to make the or to cast the deck slab here. Here there are various components. First of all, I want to explain this speed floor system first. So this is basically the section that is used for the speed floor. Here you can see that this is basically simple I section, and the bottom flange is like this and top flange is like this. So after that, this is called LGS, that is light gauge steel. So light gauge steel is also a very effective way of construction of steel buildings that is widely used in India as well as in the Middle East. So coming to the speed floor, this is basically the view here. So in this view here you can see that there are very large cutouts here just to decrease the weight of the structural steel, that is optimizing the cost. And the advantage of this holes is that you can easily pass the services along these cutouts. And this is basically the light gauge steel. So here you can see that the light gauge steel is being erected here. So it serves as the wall. So each and every like member serves as the structural steel part, and it provides the stability. That is, in simple words, what we can say is that here you can see that there are no strong columns here, that is like I section structural steel. Why there are no columns here? Because each and every member acts like a load transferring element from top to the bottom, and in addition we are also providing the bracing here. So it is like a very these are, I must say, kind of Lego blocks that we can just interlock them, and we can make a very beautiful buildings and cost effective building with the help of this approach. So this is basically the thing that I was discussing with you earlier also. Here you can see that this is basically the HRS structure, that is hot rolled steel. So these are the main columns, and these are all hot rolled structural steel sections. These are the Schnell panels or the wall panels, and this is basically the speed floor here. So here you can see that they just install the speed floor and then do the concreting over that. This is basically the typical drawing. Here you can see that these are the speed floor structural steel sections, and these are the lock bars that needs to be installed here. Here you can see that this is basically the speed floor joist. Here you can see that they just make the hot roll structural steel sections, install the Schnell panels and install the speed floor systems, and then do the concreting over them just to save time. These are basically the Schnell panels. Here you can see that this is the speed floor system bottom corridor portion. So explaining more about the speed floor, so it is basically the lighter, faster and easier. So here you can see that this is basically the joist of the speed floor, and this is called the shoe. That is, the purpose of this shoe is to transfer to integrate this joist to the main structural steel section. So they are basically the roll formed galvanized high tensile, that is 350 MPa, and usually they are 3 mm thick, and the average production or the average steel grade is 350 MPa, and this is the way with which these speed floor joists are made. These are them in the stacking yard, and here you can see that they are provided in the series of 200, 250, 300, 350 and 400 mm. So this number is basically the depth of this joist from this point to this point. So here you can see that this is the edge angle and this is the hanging angle. This is basically the plywood that is kept on the top, and these are the interlocking bars here. So here you can see these are the lock bars. This is basically the joist that we are talking about, and here you can see this is the shoe. So on this hot rolled structural steel sections, they just put this shoe of the joist from this point to this point. So the shoes are simply bolted to the joist and ready to ship. So in this example G+3 residential building at Raigad, here you can see that the joists are installed on these hot rolled structural steel sections. These are the lock bars, these are the shoes. So on the top of these joist we can put the plywood, and on the top of the plywood now we have laid the reinforcement bars here, and after that we do the concreting here. So 3 days after the concrete is poured, we can remove the shuttering system is removed, and services can pass through these pre-punched holes. And if false ceiling is required, that can also be hanged from this steel joist here. So here this is another view. So this is basically log bar, flange, service hole. So the bottom this shape acts as a tension member both during the construction phase and when the joist is acting compositely with the slab. So it is a 2-hour fire resistance also. So here you can see that the people are sitting below this speed joist system here, and below and from this joist also, here you can see the services are also hanging here. Here you can see that how the basically purpose of these holes. Here you can see that the pipings are being passed from this steel joist here, from the cutouts here. So they are also used in car parkings. Here you can see that the speed joists are installed here. See, for those who are mixing this joist beams with the basically the castellated beams, both of them are different concept. Speed joist is a different concept, and castellated beams are different concept. So here you can see that this car parking is made in the structural steel. How heavy bracings they have provided here, and they had also installed the joist here. And this is another Schnell panels, or EPS, expanded polystyrene concrete wall panels. They are also used. So that we had discussed in the earlier PPT also. And light gauge structures are also very important. That we will discuss in the next lectures, that how we can design the LGS structures also, or we can say cold roll structure steels also. So for LGS, SAP 2000 is also very good software. ETABS is not that much good in designing the cold rolled structural steel sections, because ETABS does not have those codes. But SAP 2000 do have the codes for designing this cold rolled structural steel sections, and STAD also has a code for designing. So here you can see that these are the wall panels. So the wall panels are first of all this erected here. They are just simply bolted to the foundation slab here, and accordingly they are like just connected one over the another, just like Lego blocks, and then accordingly we can make this type of building here. So after construction, before construction it was this, and after construction it is this. So you cannot easily differentiate between this building and this building. So these are the floor dead load values that has been comparison has been done, and like 10 mm ceramic tile plus 30 mm mortar and 120 mm thick concrete slab. This is the comparison. This is basically the simple wall panel that we are talking about here, and pin connection is done at the both ends. So this should be make sure there are no moment connection in this. These are the braced wall panels, load transfer details. So this is basically the practical, and this is the theoretical arrangement that we are talking about. And here you can see that the whole hostel is made in the light gauge steel arrangement here. So this is basically a 3-story 16,000 square feet structure that we are talking about, and here you can see that this is completely made in the light gauge steel arrangement here. So this like this is just like a human body, that outside it looks different, and inside there are all bones and skeletons inside. So this is basically another example of this light gauge steel construction. So this is basically the outside, and this is the inside view. Here you can see that this is the best example, that hot rolled structural steel sections are erected. After that, this LGS curtain, that is light gauge steel curtain wall, are erected here, and then accordingly we can install the speed floor system here, and on the top of that we can install the ply and then the reinforcement, and then accordingly we can do the concreting. So we can see that how much labor we can save, how much labor cost we can save, how much time we can save, and how much money we can save. So that is why this type of this light gauge steel construction is prevalent in low seismic zones. In high seismic zones, I also do not recommend to like much be dependent on this type of arrangement, but for low seismic zones they are much recommended. So here you can see that already the building was made, but maybe there was a need of the expansion. So that is why this light gauge steel walls are like casted or erected here, so that we can easily expand the floors without increasing the dead load of the steel structure. So basically the focus segment for this type of the low cost houses, residential buildings, bus and truck terminals, project offices, restaurants, shopping malls, commercial buildings, staff quarters and washrooms. So I hope now at the end of this lecture we are clear that what exactly are the practical implication of the steel structure. So in this lecture session, what we will learn is that I want to give you a basic introduction of what exactly are the cold rolled structural steel sections and cold rolled steel structures and how they can be made. And in the next lecture we shall learn how we can design that in the STAAD software also. So there are basically three prominent codes that are used for the cold rolled structural steel design. One is the American, another is the New Zealand, and the third one is the Indian code. So IS 801 is basically the code for this cold rolled structural steel design, and AISI is basically the American standard for this cold rolled structural steel designing. So that I shall explain you in the next slides, but in this slide I want to give you a brief introduction of how these cold rolled structural steel sections are made in the mill. So here you can see that this is basically the raw steel at the plant. And for this raw steel, we make out the coil rolls here. Here you can see that there are these coil rolls, and accordingly from these coils we are galvanizing them. And here you can see that these coils are now basically slated here, and when we get this coil here, we pass it in a machine, and that machine's sole purpose is to give it a particular shape. Either we can give it a C shape or either we can give it a Z shape here. So this was basically the part where we had learned how we can process this light gauge steel formwork or structural steel sections. Here this is the framing fabrication, that is after we have made them. Now here you can see that they are basically joined here, and after joining them they are basically stacked over each other, and after stacking they are basically transported to the site. Here you can see that the steel sections are loaded on the back of a truck. I must say that this is a very unsafe form of work that is being used here. I don't recommend it, because a laborer or a worker is standing on the top of this whole steel sections. So that is a very unsafe form of work, and after that they are simply transported to the site here. So here you can see that these are the LGS or curtain wall sections that we had discussed in the previous lectures. So they are just erected like this, and after that they are bolted to the ground here. So here you can see that this is a bolt and a nut, and here you can see that the engineers measuring the dimensions here, and the trusses are now installed on the top, and in this manner we can just make a small room here. So this is basically the simple thing that or the simple methodology that is made for the light gauge structural steel sections. Here you can see that this is basically the RCC building, and on the top of that we have made this light gauge steel roof. Here you can see that this is the LGS curtain wall, and on the top we have installed these LGS sections. This is again a structure that we have discussed many times in the previous lecture. So there are various approaches that is considered for the cold form structural steel design. The classical method is the effective width method here. That is basically the approach of this method is that the whole section is not considered effective. These are the areas that are considered ineffective. So after removing the ineffective area, we make a new equivalent effective section here. So with the help of this effective width method, there is a reduction in width of cross-sectional area to account for buckling effects. It is basically an analytical approach, and it involves very lengthy calculations. So this is basically the local buckling effective width concept Fy and distortion buckling effective thickness concept Fy. So here you can see this is basically the effective width method, and this is basically the effective thickness method. That is, the whole thickness is not considered to be participating in the forces. So these are basically the various type of cold form structural steel sections here. Here this is an angle, this is a Z purlin. These are again Z purlins here. This is basically C purlins or C-shaped sections. Here also you can see that these are the single open sections. These are the open built up sections, and these are the closed built up sections. And local buckling, what basically is meant by the local buckling? Local buckling is also an important criteria when we are designing the hot rolled structural steel sections, and basically the thickness of the light gauge structural steel section is very less, so local buckling effect is very much prevalent or very much dominating in the design. So it is basically typical for a cross section rather than the whole length of a member, and edges between the plate elements rotate without translation. Here you can see that the edges between the plate elements are rotating without any translation, and strong post buckling reserve and occurs at short half wavelengths here. And distortion buckling is the rotation of the flanges about the flange or web junction and lateral bending of the section. So here you can see that the local this flange just rotate about this particular point here, and here also this is another example, and here this is also another example. So it depends upon the ratio of the width of flange to depth of web. And lateral-torsional buckling. So this is basically the local buckling. Second effect is the distortional buckling. Third effect is basically the summation of this and this. So this is called lateral torsional or latero-torsional buckling. So this is also an important effect when we are designing for the hot rolled structural steel sections. So member translates laterally as well as the section rotates. So here you can see that the section is itself translating also, and it is also rotating also. Here also the section translates as well as rotates. So it is observed in open sections in which the ratio of the moment of inertia with respect to major and minor axis is very high. That is, in one direction the moment of inertia is very high, and in the minor axis the moment of inertia is very low. So in those type of sections, this lateral torsional buckling effect may dominates. So this is another example of design, that is direct strength method of design. So here you can see that the main instability of cold form steel beams are local, distortional, and lateral torsional buckling that we have already discussed in the previous slides. And direct strength method as a design is basically the reduction in effective stress to account for buckling effects, and it requires elastic buckling solutions, and expressions are empirical in the nature. So these are the three formulas here. That is, the number one formula is for the lateral torsional buckling, second formula is for the local buckling, and third formula is for the distortional buckling. So elastic buckling solution can be arrived using finite element method and finite step method, spline finite step method, and analytical expressions. So these methods can only be solved in the ANSYS, finite element and finite step method. We shall study about this in the next slide also. So these are basically the proposed draft for the IS 801 that is under consideration, and after that we shall discuss the generalized beam theory principles. So these are basically the typical results that have been made here, and these are some papers that you can download from the internet. They are available free of cost. And here this is the finite element method, this is the finite step method. So basically in the finite element method we divide this whole arrangement into various number of plates, and in the finite step method we divide this whole member into various number of strips. So this finite element method, that I shall also teach you in a separate lecture. So when we will study about this like Euler buckling loads, then I shall teach you how we can do the finite element method of analysis in the STAAD software. So after that, this is basically the buckling analysis that has been done for the lift channel column with the fixed ends here. So this graph is nothing but a very simple common sense, I must say. That is, here you can see the buckling stress, and here you can see the length. So if the length of the member is less, the buckling stress value or the the strength of the member is very high, and when we are increasing this length here, similarly the buckling stress value also decreases. So Here also we have studying the like the development of strain matrix for mode decomposition. So these are the methods that you should read when you are like too much into this cold roll structural steel sections. But just to give you a brief introduction, that is why I am showing you all the data here. So this is a very important table that is being shown here. So what exactly is what are the codes of practice for the design of structural steel? One is the AS, that is, or NZ 4600, that is Australian or New Zealand code. It was released in the year 2005, and the analytical expression that is being followed in this code is the Hancock model. After that, AISI S100, and in this basically the Schaeffer model is used. And after that, IS 801, that is Indian standard. This in Ajish and Arul 2WS 2016 model is used. In all the three codes, the finite strip method is used, and decomposition of buckling modes is considered in this IS 801 itself, and mode identification in SFSM is also considered in IS 801 itself. So these are basically the papers that you can study from the net also. And this is the provision for design of tension members, that is 0.9 ANC FU by gamma M1 plus beta AG not FY divided by gamma MO, and where beta is shown by this particular value here. So for tension member the design is different, for flexural member design is different, for tension member these are the formulas here, for compression member these are the formulas here. That is P is nothing but chi U into Ag into Fy, where chi is shown by different formulas here, and similar formula is also used in the calculation of the structural steel, where we need to calculate the phi and chi also. And after that, for flexural member these are the formulas that has been considered here. And for beam column the approach is like we do need to consider the axial force and as well as the moment. So like in the structural steel, hot rolled structural steel also, we do P by P naught plus M by M naught plus M2 by M naught, and that the whole sum should be less than or equal to 1. Similarly, we do need to consider this in the case of cold rolled structural steel sections also. And this is basically the linear interaction, and when we are considering non-linear interaction equations, the formula is different here. So this was just to give you a brief introduction of how the things work for the cold rolled structural steel sections. So in the next lecture we shall come to the basic or practical application, that how we can design the cold rolled structural steel sections in the STAAD software itself.